Hello, Earth scientists. What we're going to hope to do with this video is put a formal face on something that many of you probably arrived on your own. Certainly, somebody in your group did. But that's using a little math and a little what's called proportional reasoning to reason what the size of objects must be based on how large they appear. After all, isn't that what we're after with the angular size challenge? And isn't that what an astronomer is trying to do? Okay, use the size that something appears to be to tell us about something that it or tell us about what the size must actually be. Okay, so the idea is we can scale this up to any size that we want, and we'll look at the challenges that a real astronomer faces in a moment. But take a second, pause the video, see if you can find relationships that exist based on these four quantities that we were looking at in our lab work. And by relationships, I'm kind of saying like blah is to blah as bleh is to bleh. See if you can find some things that would work there. Okay. There's lots of things that hopefully jump out. I mean, one we could say apparent size is to sighting distance as actual size is to actual distance. Little is to little as big is to big there, right? Of course, that's not the only one that there is. Actual size is to apparent size as actual distance is to sighting distance. Okay, and maybe you found one of your own that's not one of these. So yeah, these proportions exist, and you again that might have jumped out to some people right away. That doesn't mean that measuring these things are easy. Okay, that's where science and math kind of go their own separate ways on this. Doesn't mean that measuring apparent size is something that we can do, elementary, but it does. We're going to use that mathematical basis. Okay, so let's bring that together into a single equation. Okay, and again, this is just one of many that would work. That would kind of describe some of the relationships slash ratios that are exist here. So this one I happen to choose actual size is to actual distance as apparent size is to sighting distance. Okay. And what this means mathematically is like if we can measure the apparent size of something, and we can always kind of measure the sighting distance, if we know the actual distance, then we could figure out what the actual size of that object is. And likewise, we didn't do this with our lab work. But if we knew the apparent size, we measured it, and we knew the sighting distance, and we knew the actual size of something, we could figure out how far away it is. Okay? So, in a way, there's kind of two unknowns over here. But just from the apparent size and sighting distance, which are two things that are measured comfortably from in our lab from 5 meters away, or for an astronomer from right here on Earth, we can find the size to distance ratio. Okay. We don't know the size of, let's say, Saturn from a measurement like this, nor do we know the distance, but we do know with a decent amount of confidence what the size to distance ratio is. Okay. And we're going to use this idea and some practice that you guys are going to do. But one other way that we can do this is, scientists like to use, when we're using a formula, we like to use shorthand. Um, Frequently, just because that equation that we just gave you or those relationships can get a little bit tedious. So another way you could write this is like big S is to big D, where big S represents actual size and big D is actual distance. Is um, Big S is to big D as sighting distance is to as apparent size is to sighting distance. Okay, or sometimes you'll see this written with like S1 is to D1 as S2 is to D2. Okay, just a shorthand way of getting this same idea across. And again, what we're going to exploit is that if we know any three of those, you could solve for the fourth. Okay, so of course, in real astronomy, here's the problem. Okay, the objects that we were measuring outside maybe appeared to be 5 or 6 centimeters big or 20 centimeters, or it certainly depends on what you're measuring and what your sighting distance was. But almost anything and everything that an astronomer is going to look at is going to be tiny. Okay, what I have right here pictured is what Jupiter might look like in the night sky. Okay, this little dot over here, not this circle. And that's actually being pretty generous. Okay, Jupiter at its largest, probably wouldn't even appear to be that big in the night sky. So that brings one of the reasons why an astronomer needs a telescope. I mean, one thing, and that's kind of what this circle represents here. Okay, if we view Jupiter through a telescope of a certain magnification power, it might look more like this. And besides giving us a better appreciation of the details and features of Jupiter's, and perhaps looking like Galileo did at Jupiter's moons, um, this allows us to make a much better measurement. Okay, we could measure the diameter of Jupiter here and expect to get a smaller kind of um, a smaller amount of error in our measurement. Okay. So scientists oftentimes aren't worried about how much their measurement is off from the true value as much as how that amount of being off compares to the true value. Okay. And that's kind of a mouthful. But basically, what I'm saying is looking at this magnified view right here, if I was off in my measurement by 1 millimeter, I'm trying to show that right there, that would be a fair amount of the width of what this actual measurement would be, but it'd be nothing compared to being off by a millimeter on this measurement. Okay. Over here, a millimeter is about how wide Jupiter appears to be. That'd be like 100% error because it'd be off by the entire width of my measurement. Whereas here it looks like it's about, I don't know, a 20th or so, something like that. Okay, so we literally reduce error by using this magnification and going like that. Now, what we need to do is be careful because when we magnify an image of Jupiter or a planet or of anything, um, we're magnifying the apparent size, but we can't carry that magnified apparent size through the equation that we came up with earlier. Okay, so the other thing we got to look at is what's the magnification power of our telescope, and whatever our magnified apparent size of our object is, we need to divide that measurement by the telescope's magnification power to get what's called the true apparent size. Okay, so Jupiter appears to be this size, but when we divide by the magnification power, we're going to get a number that's closer to this true apparent size of this little dot over here. Okay, so use the tool to see things clearer, but use a little bit of math to be able to work back to what we're after again, which is the true size of objects or the actual size of things. Okay, and here's what's kind of cool about the math of this. So we're saying you could measure the diameter of Jupiter using that method, but you could also measure this is a picture, and by the way, what you're going to be doing with your work is using real telescopic images. So we're doing some real applications of the stuff that we're talking here. So they're to scale, but what we're looking at here is an image of Jupiter with its Galilean moons. So those moons that Galileo saw, they're now referred to. And, we kind of give a little shout out to Galileo and the Galilean moons. But we could also use this to get this method to get an apparent distance. Okay, this first moon, Ganymede, that's the apparent distance from Jupiter's surface to that moon. And similarly, from here to here would be the distance to Europa. So I don't have to just use it for sizes of things. I can use it for apparent distances from a planet to a moon. And there's other applications beyond that. Now, there's a little to think about when we have moons that are orbiting about a planet, and I'm going to leave it to you in your work to consider some of those things. Why these measurements are could be a little bit misleading, but that's for you to think about in a bonus question. But at this point, you want to head over to those practice exercises. How can apparent size be used in astronomy? And you're going to want to either print off a ruler, uh, copy one from your screen, or hopefully you have a ruler handy while you do it, because that whole activity involves making measurements. But even if you have to copy one from a screen, you should be all right. All right. Head on over to those exercises and have a good one, you guys.